With these last few weeks of the school year, we're going to put some calculus into our pre-calculus. And the first calculus topic we're going to get into is limits. So the definition here of a limit is the value that a function, so that'd be like your y value, approaches as the input, the x value approaches a certain number. So if you look at the first diagram on the left, you'll see something that's pretty familiar. We have this black curve, and we don't know the equation of it, but we can see what it's doing. We can see that as x approaches infinity, as x gets larger and larger and larger, this function approaches zero. And we've seen that before when we've dealt with asymptotes, when we've done exponential functions and rational functions that have asymptotes. But with limits, the way we would write this is we would say, and we need to give this a name. I'm sorry. We need to call this function something, especially since we don't have an equation for it. I'm going to call it g of x. So what we can say with limits here is the limit as x approaches infinity of this function, g of x, is 0. So we know this function will never actually hit 0. There's no number that you could plug into it that would give you 0. But we know that as x gets larger and larger, that is its limit. That is the number it is constantly approaching. On the right, we have a little bit different situation. We have what's otherwise a nice smooth curve here in red, but it has this hole in it. And what's most likely happening here is that when we plug in 2, we end up with a 0 in the denominator and the whole thing falls apart. So if we were to plug in 2 to this function, which is f of x, we would not get a value. It would not exist. 2 is not part of our domain. However, we can see what the function is doing as x gets closer and closer to 2. And so that's where limits come in. We can say the limit of this function as x approaches 2 is 4. So you can see on both sides, as x gets closer and closer to 2, this curve gets closer and closer to 4. So we're going to look at a couple ways we can look at limits right now. And here's the first one. This is using a table. So I've set up this table of values that I'm going to plug into this function here in purple. And it's asking for the limit as x approaches 0. So a couple things. First of all, I can see right away if I were to plug 0 into this function, I have a problem because 0 squared is 0. So I would have a 0 on the bottom of that fraction, and I know that's not going to work. So 0 is not part of the domain. But if you look at the numbers I've chosen in this table, they are numbers that are already pretty close to 0. And as you go into the center of the table, they get closer and closer and closer. So these numbers are converging on 0. So what I want to do is plug these numbers in and see as I get closer and closer to 0, what number am I approaching? What number is my function approaching? So I've already worked all these out. And one thing I do want to point out before I start filling them in is if you look at this function, both of the places where you would plug in an x, the x is squared. So it doesn't matter if a number is positive or negative. When you plug it in, it's going to get squared and become positive. So that means when I plug in a 1, and when you plug in a 1, you should get 0.16228. And that's rounded off to 5 places after the decimal. You'll get the exact same thing when you plug in the negative 1. So that's going to be true for all of these, which is kind of nice. So I plug in 1, plug in negative 1, I get that value. Right now, that doesn't tell me anything. Because to do limits, you have to see what happens as you approach the number. So you need more values. You need to be able to see a trend. So I'm going to plug in 0.5. And when I do that, I get 0.16553. And that's going to also be true for negative 0.5. So I can tell that it's gotten bigger. Still not really enough to know where it's going. So let's keep plugging numbers in. So I'm going to plug in 0.1 this time. And when I do that, I get 0.1 0.6662. All right, so now it gets bigger again, but it gets bigger by a much smaller amount. And even though, like, from 1 to 5, that the difference there is 0.5. From 0.5 to 0.1, it's 0.4. So not too much difference there, but if you look at the rate this is increasing, it gets much, much smaller. So that tells me I probably have a curve that is bending toward a certain place, a certain value. So let's go ahead and do another one. And when I plug in 0.05, what I end up with is 0.16666. And there's no like right or wrong number of values you need to plug in to do this. And there's no like magic number as far as how close to the number you need to get. You just need to plug in enough to be able to see where it's going. Here I can see that as I get closer and closer to 0, this gets closer and closer to 0.16 with the 6 repeating. And if you weren't certain on that, you could plug in like 0.01 and see if it gets even closer to that value. So this is not a perfect system. It is just plugging in values and seeing what's happening, but it gives us a pretty good idea of what the limit is and where the function is going as x gets closer to a certain number. One last thing really quick, if you're good with repeating decimals, you may recognize this as 1/6. So that would be another way you could write that. So that's one way to do it with the table. Another way you can do it is with a graph. And so here we have this function x squared minus 1 over x minus 1. And when you graph that, it looks like this red line here. It appears just to be a straight line, a linear function. But I can see by just looking at this that if I were to plug in a 1 to this function, I get a problem because I have 1 minus 1 on the bottom, and that's going to mess everything up. So one quick diversion here. Let me hop over to Desmos. I've got this pulled up. Right here. If you go where x is equal to 1, which is right here. Oh, there it went. Right there. You can see that it tells you at 1, the function is undefined. Now, most graphing calculators, they're not going to put a little dot or a little hole right there because when they graph these, they're considering every single value. And even though 1 is undefined, 0.999999998 is not undefined. And 1.000000001 is not undefined. So you can get as close as you can possibly get to 1 and still get a value. It's just at 1 where you have a problem. So there is a missing value here, but it's like almost too tiny to be perceptible. So we're undefined at 1. The nice thing about this, though, is what we're asking for, though, is the limit. What's the limit as it approaches 1? And even though we are undefined at 1, even though we have that hole there, and I should have drawn an open circle. I don't know what I'm doing. Okay. So even though we have this hole here, this missing value, it's very clear to us just by looking at the graph that as this function, as x approaches 1, as we get closer and closer to 1, this function gets closer and closer to 2. So we'd say the limit of this function as x approaches 1 is 2. And some of these, it's very simple just to look at the graph, see where that point is, and that's it. Now, it's not always that easy, but sometimes it is. So you're just looking at the graph and seeing where it's going. All right. We also have situations where the limit doesn't exist. And I don't know if you've seen Mean Girls and if you recognize that reference. But there's two main situations we're going to be working with where the limit doesn't exist. And one is, and this comes up a lot in trig functions, is where the function oscillates, where the function goes up and down. So here, it's asking what's the limit as x approaches 0 of sine of 1 over x. And we know that because plugging in a 0 would mean putting a 0 on the bottom of that fraction, that there's going to be a hole in our graph at 0. And we could figure out, if we zoomed in on this, what the graph was doing on either side of that hole. Here's the problem, though. For it to be a limit, the function has to be steadily approaching that point. And here, when you have, and this is very dense, and it's hard to see what's going on, but what's happening on this function is it's just going up and down like this. So the function is not really approaching anything. It's just going up and down a bunch. And so when you have a function that oscillates like that, it's like a wave, it just goes up and down, you would say the limit does not exist. So these trig functions, these wave functions, they don't have limits because it's never really approaching anything. It's just bouncing up and down over and over and over again. The other time a limit would not exist would be this situation right here. And what you can see here is for this function, as x approaches -1, which is right here, we have an asymptote. And as it approaches this asymptote, the function goes to -infinity on the left, and it goes to +infinity on the right. Now, that's something we haven't seen yet, where it's doing different things on either side of the number it's approaching. And that's okay. You will sometimes see where the limit from the left side is different than the limit on the right side. But here, on both sides, it's going to +infinity or -infinity. Positive and negative infinity are concepts we use, but they're not actually numbers. They're not values that we get that we can use as a limit. So if you get something like this, where the function is going off to infinity and or -infinity, that would be another place where you'd say the limit does not exist. So for what we're doing for limits, we're not ever going to use infinity as the answer for a limit. If it's going to infinity, we would say that does not exist. So this is just kind of the basics of limits. Once you get into calculus, you'll see where this applies and how this gets used and mixed in with other things. But that's what we're going to do with it to start. We will go a little deeper, but hopefully that makes sense there. So that is limits.